In this video, you will continue learning how to solve a trigonometric equation. What we want to look at today are when you have to first combine like terms. So let's talk about what like terms are. What makes two terms like is that, first of all, they are the same function. So for instance, cosine x and 2 cosine x are both cosine, and the degree, first power on both of these, are the same. If that's the case, you can take the coefficients of those functions. So for this one, 1 cosine x and 2 cosine x, and add them together. So for instance, 1 plus 2 would be 3 cosine x. Similar, sine squared x and 3 sine squared x, I could add those together, 1 plus 3, and get 4 sine squared x. Likewise with negative tangent x and tangent x, if I add those together, a negative 1 and a positive 2 would be positive 1 tangent x. Those were all the same function with the same degrees, so you could combine their coefficients. Some unlike terms would be cosine squared and cosine x, because here we have a squared term, whereas this cosine function is only x to the first. Sine squared and 2 sine x, this sine still has a degree of 1. The sine squared is a degree of 2. Even though the coefficient is 2, these are unlike terms. Even when you have tangent cubed x and tangent of 3x, again, this tangent function has a degree of 1. This has a degree of 3. These are unlike terms. So now that we know what like terms are, let's look at some examples of how to solve with like terms and combine them. So in this example, number 1, we have cosine x and a negative cosine x. Those are like terms, so we want to start by combining them. So since I have negative cosine x on the right, I could add the opposite, so add positive cosine x to each side, canceling those out and giving me 0 on the right side. And then by combining the coefficients, 1 plus 1 gives me 2 cosine x, still plus my root 2. Then we can continue solving like we did before. We need to get the cosine x isolated. So add or subtract first. Here's subtracting root 2. Then divide each side by 2. So we're looking for where the cosine function is a negative root 2 over 2. This is when I want to bring up my unit circle. On my unit circle, if I look at the 45-degree reference angle, I can see that cosine, the x value, is root 2 over 2. So that tells me to look at the other quadrants where I have a 45-degree reference angle. I would ask you to remember that in quadrant 1, the cosine function is positive, the sine function is positive, and tangent is positive. In quadrant 2, now cosine is negative, sine is still positive, and tangent is negative. In quadrant 3, we're going to have a positive tangent, but now both cosine and sine are negative. And in quadrant 4, we're going to have a positive cosine value, negative sine, and negative tangent. Since I want negative cosine, I want to be looking in quadrants 2 and 3, again at my 45-degree reference angles. So sure enough, at 135 degrees, or in radians, 3 pi over 4, cosine is negative root 2 over 2. And at the 45-degree reference angle in quadrant 3, if I look at 225 degrees, or 5 pi over 4 radians, cosine is again negative root 2 over 2. So what that means is that x would be an answer of 3 pi over 4 or 5 pi over 4 if I'm on the interval between 0 and 2 pi, or since those values, 3 pi over 4 and 5 pi over 4, were not 1 pi or 180 degrees apart from each other, in the general form, I would have to add 2n pi. Let's now take a look at example 2. Again, I have like terms of 5 sine squared and 1 sine squared. For me to combine those, I need to get them on the same side of the equal sign. So I'm going to subtract 1 sine squared from each side. That'll cancel out everything on the right, leaving me 0. And 5 minus 1 is 4 sine squared. Now I can continue solving. So I need to add or subtract first, so we'll add my 1. Divide by 4. And I have sine squared equals 1/4. To get rid of the square, we have to take the square root of each side. And so sine of x would be, if I simplify this, first of all, remember we need a plus or minus. The square root of 1 over the square root of 4. Square root of 1 is 1. Square root of 4 is 2. So I am looking for where sine is either a positive or negative 1/2 value. Again, on our unit circles, sine is a value of 1/2 at the 30-degree reference angle. Since I want everywhere where it's positive or negative 1/2, I want to use all the 30-degree reference angles in each quadrant. And so in radians, that's going to be all of the radian measures that are over 6. And so therefore, x would equal pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 if we're talking about on the interval between 0 and 2 pi. For the general form, let's look back at our unit circle. If I write pi over 6 and just add pi, that gives me my 7 pi over 6 answer. If I take 5 pi over 6 and just add pi, I get the 11 pi over 6 answer. So we don't need to write all 4 of them. We can just write pi over 6 plus pi n and 5 pi over 6 plus pi n, and that would also cover the 7 pi over 6 and 11 pi over 6 answers. Let's now look when we have to factor out a GCF below. Here, I see that sine squared x and sine to the first power x are not like terms, but they are the same function. So I could factor out essentially a GCF. And so if we think back to more simple algebra 1, if you had the function 2x plus 4, you could factor out a GCF of 2. What you did is you took the 2x and divided by that same 2, and the 4 and divided by 2. Because again, we don't want to change the value since there's no equal sign to do on both sides of the equation. So if we're going to multiply by our GCF, we also have to divide it out. Simplifying, 2 divided by 2 leaves me with x. 4 divided by 2 leaves me with 2. Notice I had 2 terms to begin with, so I have 2 terms inside my parentheses. Also, if I were to distribute my GCF back inside the parentheses, 2 times x is 2x, 2 times 2 is 4. So let's now apply that here. We can see that our GCF is going to be the sine function. And so if I take the original 2 terms and divide by my sine function, my GCF, sine squared of x divided by sine of x is just 1 sine of x. Sine of x divided by sine of x is 1. From here, we can use our zero product property to say that sine of x is equal to 0, and that sine of x plus 1 is equal to 0, because those two terms were being multiplied equal to 0. From here, you're really just solving each one individually. So I could subtract 1 and get that sine of x is a negative 1. This one's already solved for. So what that means is on my unit circle, I'm looking for two different values now, because we had two different equations we solved. I want to know where sine is a value of 0, so at 0 and at pi. I also want to know where sine is a value of negative 1, at 3 pi over 2. All three answers are answers of our equation. So again, from 0, we got x to be both 0 and pi. And from negative 1, we got x to be 3 pi over 2, together giving us that. Now this would be our answer if we were on the interval between 0 and 2 pi. If I wanted the general form, I could take 0 and add pi n times. That would also give me my pi answer. 3 pi over 2, though, we have to add 2 pi n to. Let's now look at some examples on the next page. In example 3, you'll notice that we have a tan x in both of these. But at this point, this tan x is coupled with a cosecant squared x. So it's not right now a like term with my 2 tan x. That's why when I subtract 2 tan x over to the left side, they cancel on the right, giving me 0. But notice here, I don't combine any like terms. We're going to have to factor out a GCF of tangent x. And so when I divided this term by tan x, I was left with the cosecant squared. Dividing negative 2 tan x by tan x, I'm left with the negative 2. Now I could set each equation equal to 0 with our zero product property, solve each of them individually, and notice when you're solving this one, because it was cosecant, you had to do the reciprocal to get sine, because we don't have cosecant values on our unit circle. And also notice here, when I did that reciprocal, that left me with a radical in the denominator, which is not simplified, so I had to rationalize the denominator. And then on my unit circle, I was looking for where tangent was a value of 0 and where sine was a value of plus or minus root 2 over 2. So tangent is a value of 0 at 0 and at pi. Sine is a value of root 2 over 2 everywhere you have a 45-degree reference angle. And so that would be all of my over 4s for my radian measures. And so these are the answers that you see listed below. Again, this top answer here was for the general form. And this bottom answer would be on the interval between 0 and 2 pi. Please now pause the video and try to factor out the common term of sine from both of these terms. You should have factored out a GCF of sine x. Dividing each term by my GCF, inside the parentheses, I'm left with 1 plus cosine x. So from here, I can take my sine of x and set that equal to 0, and I can also take the 1 plus cosine x and set that equal to 0 by my zero product property. If you solve each of these, subtracting 1, I can see that I want to look on my unit circle for where sine is a value of 0 and cosine is a value of negative 1. So sine is a value of 0 at 0 and at pi, and cosine is a value of negative 1 also at pi, and so you really only have the two answers. And so x is a value of 0 or pi if we're on the interval between 0 and 2 pi, or x is 0 plus pi n times if you wanted the general form. Please now pause the video and complete example 5. Please now check your answers for example 5. You should have found a GCF of tangent of x. Factoring that out, basically dividing each term by tan x, you are left with tan x that you could set equal to 0 and tan x minus root 3 that we could set equal to 0. Solving each of these and then looking for the values of tangent of 0 and positive root 3 on my unit circle, we got the following answers. Notice in number 6 that yes, you will have to factor out a GCF, but before you do that, you do have like terms of the 3 sine squared and negative sine squared. So we want to combine like terms first if ever possible. So 3 minus 1 is 2 sine squared of x. Now we can factor out our GCF of sine x. Go ahead and finish example 6 after you pause the video. After you took out your GCF of sine of x, you are left with these two equations that you could set equal to 0, and then on your unit circle, we look for where sine was a value of 0 or where sine was a value of 1/2. Please now pause the video and complete example 7. Here, you could take out a GCF of tangent as soon as you subtracted that from the right side over to the left. That left you with these two equations that you could set equal to 0 and solve. Notice here, you did have to rationalize the denominator to be able to simplify. And so on my unit circle, tangent is a value of 0 at 0 and pi, and it's a value of positive root 3 over 3 at pi over 6 and 7 pi over 6. Again, pause the video and complete example 8. Again, you should have found a GCF of sine of x, which once you factor out, you could set each equation equal to 0, meaning I want to look on my unit circle where sine was a value of 0, which gave me 0 and pi, and where sine was a value of negative 1/2, which gave me 7 pi over 6 and 11 pi over 6.